everybody. The program you've all seen.
So I'm going to start out this morning and give you a sort of introduction overview of where we've been going with studies of early galaxies in the first 1 to 2 gigayears, and then Pascal and Richard will follow with more details. And in particular, I'd like to emphasize the special role that the HUD-F09 team, I'll show that data. This is the infrared data we got on the Hubble Ultra Deep Field, a remarkable data set that prompted a huge number of papers. So it's been a very exciting time dealing with that data set and the previous ones that underpin that. So, of course, the first thing to start out is motivation. Why are we doing this? It's pretty obvious, but let me just summarize it for you. So what are the key issues? Why is the first 1 to 2 gigayears particularly interesting? This is such a unique time in the evolution of the universe and of galaxies themselves. There was very huge growth in the halo size during this time. The first L-star galaxy halos were assembled. First metals were being formed through this period. The very first galaxies presumably formed sometime around Z of 15 or so. We haven't got to look back that far, but it's on the horizon with JWST. And of course, reionization occurred through this period, and galaxies clearly played a major role in that. So all in all, this is a period when between redshift 3 and our current limit around redshift 10, when so much was happening. And it's such a fun time to be working, and it's fun to relate the observational results with the models too. And so when the HUD-F09 dataset came out, one of the things that we did was present this as a fascinating result for the media for pushing out further in time. And folks at STSCI put together very nice images showing basically the trends with redshift with time. And it's just not all that long ago, a couple of decades, when we thought Z of 1 was really high redshift. So Hubble came along, and that changed the name of the game, pushing things out progressively with each new instrument. And I'll comment on these as I go. But it is quite remarkable how the times have changed. And of course, down here is JWST, which looks like a small increment. Trust me, this is really hard, getting from 10 out to 15 or so, and is going to take a telescope of JWST's capabilities to really do that. And of course, it will do this whole region with much higher quality data, better signal to noise, larger samples. So many things will be done there with JWST that we're only just touching the tip of the iceberg at the moment. So let me just put a little background into this about how we got here. And as you can gather, I'm going to be emphasizing the results from Hubble and from Spitzer. I thought about this, and my sense is that as I look back on the last 20 years, this and then this are the telescopes that have changed this game. Other telescopes have made significant differences, but nothing like these facilities, and particularly Hubble, in telling us about the first 1 to 2 gigayears. And as I mentioned here, so we should get good results from these. The current cost for Hubble over its lifetime is $12 billion in current dollars. This is an astonishing amount of money. Doesn't even include launch costs for the shuttle. The nation is investing a huge amount in astronomy, and it is interesting to remember that. It came very much home to me with iterations in trying to keep JWST alive in the last couple of years, just how much money this is and how hard it is to convince people that it's worth doing. Spitzer, much cheaper telescope, couple of $1 billion worth, but still real money. And the other thing that I always remember as I look back on these various facilities is just how long it takes us to get them from when they were first conceived to actually launch. 30 years for Hubble, even Spitzer 25 years. And you'll see JWST is even longer. And as I mentioned, Z of 1 galaxies were high redshift before Hubble. What really made the difference initially in our thinking was looking at these fields. Bob Williams and other directors over time, both at STSCI and elsewhere, have played a huge role in helping us gain insights into the early universe with their choice of deep field studies. These are public data sets that really revolutionized the field. High quality data, high spatial resolution, and what has really opened it up, of course, is the ability to do photometric redshifts for very large samples, well defined statistically and well understood volumes. And so the techniques we use and are inherent in all the techniques that everybody uses photometric redshifts is the Lyman breaks. Lyman limit, Lyman alpha break at high redshift, and the signal that comes from these. One of the things that is a key problem in this area and continues to be a problem is contamination. One has to pay a huge amount of emphasis, time, effort on limiting the contamination in samples. And one of the things that we've learned, most everybody has learned, but still some teams make a mistake here, is that having deep images redwood of the break and shallower images bluewood is not going to get you large, reliable samples. Samples with 50% contamination rate are just not particularly useful. So the contamination rate is a key issue. Redshift 8 was a real goal for new cameras as they came along, and the wide field camera 3 was the camera that made a huge difference in this area. Again, just emphasizing how much is invested in these facilities. Over $1.5 billion was invested in this servicing mission, excluding launch costs, and the instrument, including the instrument. And so these are phenomenally expensive facilities and capabilities that we're using. But fortunately, they really have made a huge difference, and we can demonstrate to the taxpayer, to Congress, to the administration, that great science is coming out of these. And one of the reasons is that we put instruments on that have a huge gain in discovery efficiency. WIF3 is 40 times NICMOS. So what took 100 orbits to find with NICMOS, typically we now can find in a couple of orbits. And just in finding Z of 6.5 galaxies and greater, NICMOS managed to find 12 in 10 years, 20 in the first 2 weeks, and then over 100 galaxies in 2 years. So these gains of an order of magnitude or more just lead to astonishing new results. And just as an example of this, let me just flick back and forward on this. The HUDF, the WIF3 image is half the time, but what is clear is that the signal to noise is dramatically higher. So this is the sort of gain that one can get out of these data sets, including the area. Discovery efficiency also includes the area. And there's a factor of, I can't remember, 6, 5, something like that, in area difference between NICMOS and WIF3. So the other aspect of this, as I alluded to before, were public data sets. And the space telescopes have opened up this concept and made it a norm, essentially, for deep fields. With the HDF with Bob Williams, then the UDF and Goods, Steve Beckwith, and this whole CDF South area took the directors of these 3 major observatories with common goals and interests, maybe not coordinated fully, but the sense that these data sets with zero proprietary time enable a huge range of science and are very important for the field. And just to give you a sense of this, here, just for the CDF South region, these are all the public data sets. And they go back, started with Chandra, and right through to one set now, which is not public. This is the first ever one. But all the previous data sets were immediately public and open up the ability for a large number of groups to get in there and do work right at the forefront. And to give you a sense, this is a small region of the sky, just dumping it on the moon, but to give you a sense of the investment in just this area, there's 2/3 of a year of Hubble time has gone into this, and 1/3 of a year each on Chandra and Spitzer in this one area. If I look at the costs of these missions amortized into an hourly basis, work it out, it's $400 million of taxpayers' money has effectively been spent on this region of the sky. This alone, I think, justifies the claim that these really should be public, non-proprietary data sets that are available for all. And there's good scientific reasons for doing that as well. So what have we learned? Let me walk through this and just give some highlights, and Richard and Pascal will give more details. But the goal is to gain a quantitative census of galaxies at high redshift. Redshifts greater than 3 from these deep fields, wide fields, clusters, whatever we can. We're agnostic as to the source of data and the type of the data. Whatever is valuable will go in there and be used. And the samples are getting very large. Thousands of galaxies at redshifts 4 and 5, and hundreds at even 7 and 8. And remember, just 2 years ago, 2.5 years ago, redshift 8 galaxies were not discovered. Basically one behind a cluster. And trying to push out beyond that, though, is hard work. This made a huge difference, getting this infrared data from Wide Field Camera 3, as I mentioned. And the advantage of having the public data set, I think, was immediately obvious to a lot of people, just with the number of papers that came out in the first 3 months. 10 papers on results from this field. And the competition spurred a lot of activity, but it also enabled a lot of cross-comparison and ensuring that the data sets, the results had veracity, quality, etc. And this area is now something like 40 papers in a little under 3 years, and about half of those from our team. And there'll be a further image that will take this deeper, which will be taken over the next few months. So why is it important to go faint? It's crucial, as it turns out, at high redshift, because as we've found, the luminosity functions are very steep. The bulk of the mass and the light at high redshift is in low luminosity galaxies. Nice analogy here with iceberg. This is what the deep surveys reveal, and the wider field, shallower surveys. They have great value for the bright M, which is very important to understand, but if you really want to look at the bulk of the mass and the light in the early universe, you have to be in this regime down here, faint. And that's hard. It means you've got to go deep, and it means the areas are not large, unfortunately. And to get away from cosmic variance, you need multiple areas. It's a challenge to get the time that's needed to do this right. JWST will do it wonderfully well, but it's basically an infrared telescope. And so there's the concern, as I'll mention later too, about doing this in the optical. So to show luminosity functions, Richard will certainly talk more about this and the trends and how steep the slopes are here. Just for interest, -2 is divergent. Of course, there's not galaxies of arbitrarily small size, so it's not truly divergent. But these steep slopes lead to a lot of flux, which is an important issue for reionization. There's another very important result which is coming out of the accurate colors that we can measure for faint objects at high redshift. This is another example of the value of space data where you want to do accurate photometry for large samples. And looking at the trends with luminosity and redshift in the ultraviolet colors, and using these parameters like beta and trying to understand what this is telling us about galaxies. Current thinking is that this is most sensitive to dust and is probably indicative of changing dust levels, down to the point where the extinction is essentially 0 for lower luminosity galaxies and for essentially all high redshift galaxies except the brightest ones. And so very low dust content is the most plausible and likely explanation for this. So given these results, one can integrate up and look at the integrated luminosity density in the universe in the ultraviolet, and then given our assessment of the role that dust is playing or not playing, one can then look at correcting the flux to get a star formation rate. I'm always astonished that we have been able to do this as a result of the last decade's worth of observations, that we can integrate up the total flux in the universe and get a sense of the overall star formation rate back from 600 million years or so to the current day. So mass is a key parameter for the comparison with the models, and one of the basic parameters we'd like to understand. And here is where Spitzer comes in and plays an incredibly important role. And pushing that out to high redshift is also important to look at the trends. And it still astonishes me that this little 85 centimetre telescope can actually go out and individually detect redshift 8 galaxies. We can expand the sample by stacking analysis, a very valuable approach, but we're also wanting to push deeper as well and to try and measure more objects directly at 7 and 8, and are certainly starting to do that. And I think Pascal, are you going to show something on that? Yes, that's good. And so these data have enabled us to calibrate masses and look at mass functions at redshift 4. Okay. And then take these at various redshifts and establish the mass density. And a number of folks, Stark, others, have played a major role in this as well over the last few years. So I'll move through some of these a little more quickly because I do want to get to a couple of points, key points at the end. This, I think, was shown by Valentino at probably this meeting a couple of years ago and got a lot of interest looking at the specific star formation rate trend. These are the points that were shown then, much flatter than expected from the models. And these data were, in a sense, a preliminary assessment. There was very little correction. There was no correction for dust. Preliminary mass estimates, one of the things that we have now done is Richard went away and did an assessment of the dust content and the change that would make. It basically just moved these points up. Now we're looking at the effect of different star formation histories and correcting for emission lines. And the overall change greater than redshift 3 is still fairly flat. There's a slight trend, but certainly less than the typical models would suggest. So this is evolving, as it were, but not changing greatly. So let me just say a few things about the highest redshift galaxies. These sort of are pointers to what we will see with JWST, and it's always fun to push out to see how far back in time we can go, how close to the first galaxies. Did this with a sample around 8.5, but this was the one that was the most fun, finding a redshift 10 galaxy and trying to make sure we got a good galaxy, especially after our first unlucky miss or unfortunate experience where we've learned a lot about spurious sources by finding 3 which then subsequently went away. So one of the joys of this game is working the data hard but also learning hard too when things go wrong. So this one was published in Nature, single detection H-band, but very nice limits from IRAC helped a lot, and then consistent detections. And reanalysis by Pascal with some little additional data and some looking at lower redshift contamination have strengthened our view that this is a real object. But of course, we'll just wait for Richard Ellis to get his data and confirm that it's true. We'll see, probably in the next month. Oh, this was the press release. But one of the things that is very recent here was we're looking at a new IRAC data set. And Labbé has been looking at this and potential for a marginal detection, but that's not so interesting as the fact that it probably is possible to detect this, unless it's very young, with IRAC, with very deep new data, which we hope to get. So we'll have to see how the current round of proposals goes. And it's interesting because this is already, even with the limits in one object, even the limits would do. Suggesting a change in the trend here around redshift 10, maybe consistent with some of the expectations from theory, but it's nice to be trying to probe this, and it would be good to add a galaxy or two to this sample. Okay, so let me say a few words about JWST and then just a few about the surveys. So JWST is clearly going to make a huge difference. It's one of those projects that started ages ago. I remember this only too well, and in many ways you can attribute this to the prompting of Riccardo Giacconi. He had a lot of experience with space projects and how long they took. And he said to us 3 years before Hubble launched, so what's going to happen after Hubble? And so several of us got together and started thinking about this and came up with the concept of a passively cooled, predominantly infrared telescope that we wanted it to do UV and optical. And so quite a bit of work was done around that time. Even a panel in the decadal survey recommended that this be done in 1990. The overall committee turned it down. But what was amusing from my view of this, especially having been involved in the budget crisis with JWST in the last few years, was we did an estimate as a group with some input from folks, and we thought $2 billion in 1990 dollars would be appropriate for a 6-meter passively cooled telescope. This turns out to be, in current dollars, between 3.6 and 5.3, depending on the inflator, which is an awful lot closer than the decadal survey a decade later actually came up with, which was $1 billion, which would be 1.3 or 1.6. And as you know, JW is now 8.8 life cycle cost. So it was just interesting to look back on those old discussions. So if you have people ask you about what JWST is, go through the numbers. It's 1,000 times Spitzer. When I did the numbers, I get 50 times Hubble. But Senator Mikulski wrote a letter to the administrator saying it was 100 times Hubble. So who am I to disagree? So I use 100, since that's what Senator Mikulski said it was. And I'm happy to support her support, as it were. Okay, David, I'm going to take a couple of minutes on this. Yes, thank you. And just say a little bit about thoughts of the future, because JWST is on my mind a lot, and on quite a few people's. How are we going to maximize the return? 5-year life, $8 billion, we better do good on that mission scientifically. It may have a 10-year life, but it's only being spec'd for 5 years. That's a lot of money per year. So how do we go about putting in place the data sets that are needed that will optimize the science return on that? Wide field data is great. We're enthusiastically in there. I think we have 6 papers involved. The Candles team is working hard on this with a whole bunch of papers. It's wonderful data sets. And it does a whole lot of stuff really well. But what it doesn't do is do really deep observations for probing the luminosity function, faint galaxies, very high redshift. So it's a wonderful data set, but it's not all that's needed. So let's look at another option. Lensing clusters. This comes up a lot. I love these things. These produce some of the most spectacular images going. And it's fun to look at magnified high redshift galaxies. I remember this one from the highest redshift galaxy ever at 4.9 for, I think, 6 months back in the mid-90s. So this is great, but it's unfortunately a very challenging approach to looking at distant galaxies. So Richard and I and a few other people were looking at this a couple of years ago. Here is a map of image of 1689 with magnification maps from 5 different authors. I think you could reasonably say these don't agree very well. And here actually is a comparison of taking one of these as a reference and comparing the magnifications as a function of magnification, the dispersion in the magnifications. You can see a factor of 2 is typical for the uncertainty from the magnifications. So while they're great for detecting individual objects, they sure aren't good for doing statistically robust samples accurately. Large numbers are not in this field and not in this approach, and nor are highly accurate results. In fact, I would say that it's both inefficient and inaccurate. And there's a lot of people who make very strong claims about this, which is unfortunate. I love this stuff. It's great, but I think we need to be very honest and open about what it is that you can use certain techniques for. And this is not to be used for significant samples of high redshift galaxies where you need accurate volumes with the current technology and modeling. So we need to get to deep fields. So let me just say this. We basically only have one very deep field at this stage. I'm very worried about going into JWST EPIC with one. JWST does not do optical UV data. Near infrared, yes. And so, unfortunately, it's proving hard to get people to focus on this particular aspect. I know we're all worried about next year's grant and next year's funding for students, etc., but it deeply concerns me that we're spending $8 billion on a telescope. We, the nation, Congress, the taxpayer, not us. We're the recipients of that. Looking at going into this with very few deep data sets. And it's hard at this point. Richard Ellis's program is adding 128 orbits in the near-infrared. We'd like to add both infrared and optical data. But even with 128 orbits, we're not changing the numbers greatly. This needs a substantial investment. And it's something that I hope the community, STSCI, can come together on and try and use HST in a way that is will set things up well for the JWST era. Okay, so let me finish. This is the last slide. I've gone over, David, sorry. But I think JWST really should be on our minds a lot and preparing for it. Even though, as I said, we're all worried about getting the next paper out, our students, getting grant runs, etc. We have a responsibility to the nation to do really well by this telescope. And so we need to think carefully about that. So I think additional deep fields are needed. I think it's really important that they be open and fully available. I haven't said anything about ground-based telescopes. I think there's some great opportunities coming up, but it's really only now that we're starting to get the capability where it's going to make a difference at high redshift. Mossfire is one aspect of that. Okay, so I'm sorry I went over. Thank you very much, David.
I think maybe just a couple questions, and we'll take it out of our break. Sandy.
Could you be quantitative about what a proper HST optical program would look like, or infrared optical?
I think that one is looking at MCT scale activity. So it's not something we haven't done before. I mean, you're deeply involved in one of them, the CLASH team. So it's 500,000 orbits would make a substantial difference. And so, Matt is certainly worried about this as well, because he's Matt Mountain, very cognizant of the political environment. And that was a proposal that we put together for the last round was actually of that size. It was 600 orbits, 3-year program to try and do deep fields in every candles field, which is the obvious place. There's wide area, in sort of intermediate, deeper areas, and then some deep fields in there would be marvelous. Multi-wavelength data set with a full range of depths. That's ideal.
One more question. Oh, good. All right, we'll just move on. Pascal?
Good.
Oh, great.